everybody, welcome to your exam 4 review. Okay, so isn't that crazy? We're already in exam 4. This is going to be over chapters 9 and 10. Of course, we'll have previous elements as well. It's always building on itself. And then for your final, we'll go over 11 and 12, but we'll also have cumulative questions as well. Okay, so before we get started, I wanted to just kind of go over what we've learned so far in 9 and 10, which may seem like a lot, but it's actually not too bad when you try to reconstruct it. So for example, we talked about primary alcohols and secondary and tertiary alcohols. All right, I was gonna split this into two things, but I think with my pen, I better just stick with the primary for now, so I have a little more space. So for example, if you have an alcohol like this, which would be considered primary, it's attached to a carbon that's attached to just one carbon, right? We could do a few things with this. We could do an elimination reaction. If you reacted with H2SO4, TSOH, or POCl3 and pyridine, we would get an E2 reaction. We're kind of used to 2s happening when you have a primary something, so hopefully it's not too bad. And the basic idea behind this is that these guys all make this alcohol a better leaving group. This alcohol takes on an H, or it takes on an OCl, which would be OCl2 once it attaches, or it takes on this TSO. No matter what, it becomes a better leaving group, and then hydrogen from here is taken, and you're able to get the alkene. Okay, so that would be the E2 reactions. Now you could also go crazy with an HX or SOCl2 or phosphorus tribromide. And in all three of these situations, it would react via an SN2 reaction. Primary only will do SN2. We already knew that though. And you get whatever X you were trying to put on there. In this case, it would be Br with a PBr3. In this case, it would be SOCl2. And in this case, it would be whatever X you're trying to add. If you remember, Cl is difficult to use, so this you usually use for like Br or I, let's say. If you want to add Cl, well, actually, we'll talk about it in the next one in a little bit. Okay, so those are the two main things that you're going to do with primary. Either you're going to eliminate or you're going to do some kind of substitution. Okay, we also have secondary or tertiary alcohols, so let me do this. So for secondary or tertiary alcohols, let's go ahead and draw a different alcohol. Let's say we got something like this. And by the way, SN2, remember that this will always be the inversion product when we do SN2. So you only get one product. All right, with secondary and tertiary alcohols, if we start with this, we can do an elimination reaction via the following. You can use H2SO4. You can use TSOH, same exact thing. Or you can use I should have put an or up here, or POCl3. The exact same ones. But because it's secondary or tertiary, this one is going to occur, these two at least, will occur via E1. And this one will occur via E2. And you get this product. Yes, you would have a minor product, and same situation up here if there happened to have been something that was minor, but this would be the major product you would get. Then we have substitution reactions. So we could react it with HX or SOCl3 or SOCl2, excuse me. Oh, it actually should be Cl2 or PBr3. in HX, this will recur via SN1. So here you'll get the racemic mixture. Right, so you'll get the inversion, or you'll get two products, one R, one S. But these two will be via SN2. So you'll only get the inversion. But no matter what, you're going to put an X on the more substituted spot right there. Something to think about, only SN1. So when I say racemic, that means at one point it was a cation. So only in SN1 can you have the shifts. Remember, if we have an H shift or a whole allyl shift, or a whole alkyl shift, excuse me, you can shift it if and only if you have a cation, a positive charge on the carbon. Okay. So that's the only place that it happens, and the rest of these hopefully aren't too freaky, at least yet. All right, let's move on to, that was pretty much a full summary of chapter 9, by the way. Let's move on to chapter 10. I didn't include epoxides over here, so maybe it'd be worth talking about a brief epoxide. You could do something like this, and if we react it with like an HX, this is a little bit different than in chapter 10, where we have an alcohol and an X. We've always put the alcohol in the more substituted spot, right? But that won't be the case in this situation. When you have an epoxide, what you're going to get, so this would grab the H, making it a good leaving group, and the X can come in and attack. So X will come in like this, and that will go up there, and that's why you'll end up with a OH there, and our X would be down here. So here we'd get an inversion product. So that kind of acts like SN2, even though it's tertiary. But it's also an addition, really, because you're adding something. So this is that one where we talked about, it's like, it's half and half. It's kind of SN1, kind of SN2, but it's addition. So this is its own thing. So this is also just one to kind of keep in mind. And when I say inversion, what I mean by that is if you have like, let's say we have this, and we do that, you'll end up with that and that. Okay. Hopefully that helps summarize chapter 9. Sorry, I should have probably included something like that in there. Well, let's move on to chapter 10. Okay, in chapter 10, we learned a series of reactions that occur with alkenes, right? And there's pretty much one idea, which is if you form a carbocation, then you're going to get the inversion products, kind of very similar to what we've already talked about. By inversion products, I should say, you don't get the inversion products, you get the enantiomers. So I kind of drew it like this, just so it makes it a little better. And what we're going to do is we're going to take this sucker and we're going to react it with a whole bunch of stuff and see what happens to kind of help keep things straight. So if we react this with HX, you are going to get if this remains here, you get the X there. The X will always go on the more substituted thing. And you'll also get the inversion. Okay. So again, X on more substituted thing. Let's do it again. Let's do another one, and we'll just keep going until this paper is full. Let's go ahead and react this alkene. with H2O and H2SO4. Do you remember that adds an alcohol? And the alcohol in this case will be added to the more substituted thing. You'll also get the inversion. So OH will be added to the more substituted. And pretty much any time you have these two products, what that means is that you have a chance for that cation to move. So we can have shifts anytime. The same is true for the last thing that we just did. I don't know where it went. It went here. Anytime you have a racemic mixture, that means shifts can occur. So here we have a racemic mixture. Here we have the racemic mixture. Anytime you have a racemic mixture, shifts can occur. Let's keep moving. Let's react it with like Cl2, Br2, I2, etc. Mostly Cl2 and Br2, I2 we know is a very weak base, and just the premise behind this is oftentimes things grab hydrogens. Okay, so we got this, and we are going to form, the X will go on either side. So if we start off with this methyl group in the same position, you'll get an X there, and the X over here must be added on a wedge, okay? So you get the vicinal halogen, but you need to make sure that they're opposite of each other. They're anti-periplanar, right? So if we get that methyl group and does a backside attack, that methyl group will shift to a dash, and now your X here is on a wedge, which means this one has to be on a dash. So always get the anti-vicinal dihalide. All right, now let's take this and keep going. It doesn't end. Woohoo! This is before we even get to the review itself. All right, if we take that X2, so this really was just an X2, right? I just wrote X to X. If we take this X2 and add water, that's where we get the alcohol in the X. And just remember, the alcohol takes preference and it gets to go on the more substituted thing. And that X will be added in anti-fashion. Plus, or and, we'll also get the opposite of this diastereomer over here. So we'll get this. Actually, it's an enantiomer, my bad. Just make sure the O and the H are always opposite, just like the X's and the X's here were always opposite. Here the OH is on the more substituted. I like this because if you remember, this is a precursor to an epoxide. So for example, I can just do it just because we're on it. If you have these things, and you've got an OH, and you have an X, and you react it with like NaH, or you could also do NH2, or NH2 negative. Remember, this is a hydride. This H essentially makes this thing an O negative. It's the electrons here grab that, those electrons go on there, and you end up with this X with an O negative on it. Cool. And now this O negative, remember this X is polar, so it's pulling electrons away, which means that this carbon is partially positive. And so now these electrons here can come down and go whoota, and capture. And that's how you're going to get an epoxide. Like that. Okay. So just keep that in mind. Whenever you have an OH and an X next to each other, you can form an epoxide. All right, let's keep it going. We're almost done. Got one more. That's it. One more time when we have this. We've always been putting the thing on the most substituted, so the OH goes on the more substituted carbon, but you can put the alcohol on the less substituted carbon if you use that one method where we first reacted with BH3. Right? Which would keep that, but our BH2 would be like that. Of course, we'd still have the methyl group that I love to leave out for you guys. I know I'm the worst, I'm sorry. Okay, and then you could react that with H2O2 and OH minus. And what it's going to do is it's going to keep this same exact configuration. So when we did the BH2, by the way, you got the other product as well. And when you react it with OH, you get a retention of that same product. So what was on a wedge will still be on a wedge. What was on a dash will still be on a dash. Boom. All right, so those are pretty much the summaries that I can think of. Obviously, there's hours of lecture, so it's easy for me to miss something, but if I had to summarize the main points, that would be it. Okay, let's keep moving. Let's do this practice exam, shall we? Okay, so here's the review. Says, what is the IUPAC name of this compound? Well, it's an alcohol. So I can get a lot of it down, but also notice that it has a stereogenic center, meaning I've got to use RRS configuration. We haven't done it in a bit, so that's kind of why I threw this problem on there, just to remind ourselves of how it works. When I go to look at it, I've got 1, 2, 3, 4, 5. I've got a pentane. You always want to put the alcohol on the lower substituted one, but it happens to be in the middle. On the lower substitute one. Let me rephrase that. Your alcohol, you want to, whatever side it is, that's where you want to start your numbering, okay? But it happens to be in the middle. And so we can start numbering here, so we get a lower number for these dimethyls here. So we got 1, 2, 3, 4, 5. Okay. I hope you agree we have a 2, 2 dimethyl. There and there. And this would be a 3-ol. It's pentane, so it would be pentan. We don't put the E at the end. 3-ol. And last but not least, we have to worry about the configuration. If we do priority, we have 1, 2, 3. So we go like this. 1, just kidding. 2, 3. This obviously has a lot more carbon to, this carbon's bonded to 2 carbons, this carbon's bonded to 1. Okay, so this gets a bigger priority. So you go like this, and this is counterclockwise, but because the hydrogen's on a wedge, we have to switch it to the opposite. So remember, if the hydrogen had been on a dash in the back, it would have been okay, but it's not, it's on a wedge, so we switch. So 1, 2, 3, right now we're currently going clockwise. When we switch, or we're currently going counterclockwise, when we switch, we are going clockwise, it's going like this. That, if you remember, clocks are right, and that's why that is R. I didn't do any examples. Maybe in class we can come up with some if you have any, but make sure you know the E and Z naming, thiols as well, which work very similar to this, and alkenes as well. Okay, let's just get into it. So hopefully we have a general idea of how these go now, and we did already go through several example problems here. We're starting off with this primary alcohol. Essentially we're saying this thing is reacting with all of these, and we want to know what it forms. Okay, so with H2SO4, if you have these memorized, you can be like, oh, H2SO4 will be an elimination reaction, E2 specifically. And so it's really helpful to have those down because we know, whoops, that it's going to be an E2 reaction, elimination. We do the same thing here, NaH. Do you remember that that forms the nice little nucleophile there? So that would be our product. I guess I'm just going to write the products here. Okay. HCl. Remember when I said HCl doesn't like to go very easily? It doesn't like to react very easily in these situations with a primary. So you add ZnCl2 and that will force it to put a chlorine on a primary. Okay. Forces primary. All right, then we can move on to the next one. We've got HBr. This we didn't need to add ZnCl2. We didn't need anything to force it. It can just go. We get Br. For SlCl2 and pyridine, this is another way to put a chlorine on a primary. For PBr3, we're putting a bromine on it. Now this is one I failed to do. Fail. I'm sorry. Let's do it. So the main thing that's going to occur when you react TSCl with pyridine is essentially that tosyl group is going to attach to the oxygen that was originally there. So we had an OH. You're going to get what's called an OTS group, and this is a really good leaving group. So you can follow it up with a nucleophile. You could do an E1 or E2 reaction. This makes it a really good leaving group. And that's the whole purpose behind these alcohol reactions anyways, is we're trying to always add a good leaving group to them. Okay. Ah, there it is. I thought I got the wrong review I'm doing. Okay, then we move on to this next one. Let's go through this one by one. So just a reminder, we're starting with this alcohol. I kind of didn't do that in any of these situations. We've got an alcohol. We're adding the NaOH, which we know when we add sodium hydride to it, it's going to take this hydrogen and make it a good nucleophile. And the cool thing about this is this we're used to. We're used to working with good nucleophiles via SN2 reactions. And that's exactly what's going to occur. But instead of this being one of the things that we add to an alkyl halide, now we're adding the alkyl halide to it. So essentially we have a Br like this, that's ethylene bromide, or ethyl bromide. And so what's gonna happen is this can attack that, and the leaving group can leave. And we get an ether. Isn't that cool? So definitely keep this in mind. Whenever you have an ether, this is a good way to synthesize it. And pretty much the only way that we really talked about in detail. Okay, now we have this, and I'm glad we threw this one in there because we know that when we react it first, we get this OTS, which is a good leaving group. And now we're reacting it with NaSH. Remember, NaSH, we ignore the Na. This is just SH negative, which is a great nucleophile. Now the S electrons can go ahead and attack this carbon, and that would pop off. Okay, and this is all occurring via SN2. So we get the inversion product if it becomes necessary. Okay, and last but not least, POCl3. Don't get this and that confused. Okay, this is very different. P pulls off the oxygen. Maybe that's how I remember it. Okay, so even though they look very similar, P is the one that's pulling it off. All right, and so we're gonna get just a straight up E2. All right, so hopefully that helps. Well, let's keep it going. Now that I found my, oh, I thought I did. Okay, moving on to page 2. Okay, we have, I like this because now we have to be focused on stereochemistry. We have to look and think of things if they're primary, secondary, etc. So for example, it might even help you if you have some list that's like this. So you can be like, oh, that's secondary, that's primary, that's secondary, that's tertiary, and that's secondary, or yeah, secondary. So that's gonna help you right away kind of identify what's going to happen in which one. This one's primary. Remember HCl plus the zinc chloride. We already know that that's gonna force a chloride in place, and that's the only time you can put a chloride on an alcohol is when you add that zinc chloride or you do the SOCl too. Okay, so let's go through these. I've got a secondary. Pretty much anytime we've had secondary or tertiaries, that's when you've gotten the racemic when we're talking about HBr. So that's what we're gonna get. We're gonna get a racemic mixture. So we'll have one where the Br, oops, I didn't need to draw that. Pretend that's not there. One where the Br is on a wedge, and one where the Br is on a dash. This, by the way, is the wedge, and that's the dash. Don't listen to the words coming out of my mouth. Okay, here again, now you're forcing that Cl on there, but this would be occur via Sn. So this one is Sn1. This would be occur via Sn2. And so you're going to get just the inversion. What I mean by that is you can just do a direct replacement of the Cl on from the OH, but just switch the H and the D. So we'll put a D here and an H here. Remember, D is just heavy deuterium. It's just heavy hydrogen. So it's just an isotope of hydrogen, but it acts exactly the same. Okay, now for C, SOCl2 and pyridine, that's going to be a direct replacement. Right? But SOCl2 and pyridine was one way to force chlorine onto primary carbons or primary alcohols. It can also force a chlorine onto a secondary. So this is actually going to be more SN2-ish, and you're going to get the inversion. All right, and this one, remember that this TSCl is going to make this a good leaving group, and then I minus can come in, and this reacts via SN2. So in this, we'll get just the inversion product. Essentially SN2. And you'll just get an I there. Remember, Ki is just K plus and an I minus. We have an HBr on a tertiary. That's when you should be thinking, hey, we'll get a racemic mixture. And in fact, you will. So we'll get one where the bromide's on the wedge, and one where the bromide's on the dash. Okay, last but not least, we have an HCl, just like the HBr. HCl is the secondary. If it weren't secondary, if we notice the difference between these two. Here we have a secondary SOCl2 to put a Cl, and you only get one. If you want the inversion, use HCl. So you get both stereoisomers here. One will have a Cl there on a wedge, and the other will have the Cl on a dash. Cool beans, I hope. Okay, let me get some more paper. Okay, so there we go. It says devise a synthesis of each product from the given starting material. More than one step is required. Okay, so on this first one, I see I've got a primary alcohol going to a secondary alcohol. My first thought is I know how to make a secondary alcohol if I have like an alkene. I don't know how to just straight up shift an alcohol over. You don't think you can do that? So what we're gonna have to do instead is maybe first make this an alkene. So what I mean by that is I know that if I have like this and I react it with H2SO4 and water, I know that that alcohol will go on the more substituted one, and so I'll end up with this thing. Okay? But my question is, how do I get here? Well, I think we actually know how to get a primary alcohol to this, and it could be via an SN2 reaction, or excuse me, via E2 reaction, and we know several E2 reactions that will do it. So we could do a variety. We could say H2SO4. We could say the TSOH. If you remember, POCl3 will even do it. So all three of these will take a primary alcohol and make it into this, and then we can get that. There's another method too, just we could throw it out there. You could say take some stuff we already know. So let's go like this. We could replace this with a bromide, for example. And you could do that via a variety of methods. We could do HBr. It wouldn't need the zinc chloride for that situation. You could do HBr, you can do PBr3. That's the two I can think of. So let's do it. Let's take a PBr3 or HBr. And what that would do is put a bromide on there. All right, from a bromide, we can force an E2 reaction, if you remember, if we use like a bulky base. So like OCCH3. And then that bulky base will attack this carbon, and this thing will come off. Or excuse me, this bulky base, it can't attack the carbon because it's too bulky. It will grab a hydrogen here, and the hydrogen will come down. So it'll go like this, grab the hydrogen, and then the hydrogen bond will come there, and it'll force that sucker off like that. And so we can get the exact same E2 right there. And then, once again, you can use H2SO4 and H2O. And we know that that will force the alcohol. Force the alcohol up here. I don't know why I drew that. All right, if we wanted to put the alcohol on the primary, remember that's where we have to use the BH3. All right, so there's just two ways to do it. There's lots of different ways that we could do it. Let's move on to B. So in B, it says take this bromide, this alkyl bromide here, that's secondary, and it wants us to make what looks like a primary ether. All right, cool beans. We talked about how to make an ether. We know how to make an ether. If we can get like some kind of O negative on here, or OH, if we can get an alcohol in a primary and then turn it to, so what I'm thinking right now, what's in my head is if we put an alcohol on that, so like if we have some kind of do OH, and then we react it with that NaH, we can get do with an O negative, and then we can take a methyl bromide, and this will attack that carbon, and that's how we can get this. So that's kind of what I'm thinking. Remember, we talked about ethers. This is pretty much the only way that we know how to get ethers is through this method right here. But in order to do that, we have to get this thing on primary. So my first thought is we have to get rid of this bromide and make it some kind of alkene, because if we can make it an alkene, we can get to the primary. So let's go ahead and do that. We know that we can force this to occur via E2 method if we use a bulky base. So like AOC, CH3, this tert-butoxide. Again, this will grab one of the hydrogens, force this down, that comes off via E2, and we'll get that, okay? Now we're in good spot because we know how to take this after the recent chapter. We know how to take this thing and add alcohol to the primary position. And the only way to do it is through two methods. First, we have to do the BH3, which adds the BH2 to the end. Then we have to do H2O2 in water, or excuse me, an OH minus. And that will add the OH in a direct replacement. Now we're in OH town. Now we got where we want it to go. And now we can take this and react it with sodium hydride. That will give us that. And then kind of like we said, now we can take this and react it with this methyl part connected to a bromine, also known as methyl bromide, and it will give us that via just a regular old SN2 reaction. So that was kind of fun. I like that one a lot. All right, so be prepared to have synthesis. You have to know how you can take one reaction and turn it into something else. Let's continue along those thoughts and lines with the next question. So here it says prepare for each of the following from an alkene. So use any reagents you would like. So any alkene, any reagents we'd like. So that makes it kind of fun. So right away I see this. We added 2 chlorines to it. Looks like you're adding a vinyl chloride to an alkene. If that's how we're going to do it, let's just start off with, let's just make it simple on ourselves. And add Cl2. That's going to add it to each side. Remember, it would add it in a racemic mixture, right? But that doesn't matter. It doesn't talk about stereochemistry over here. If it does come to stereochemistry, then all things are going to be really fun for you. Here we have this thing, and it wants us to add a bromide to some kind of alkyl or some kind of alkene. I don't know, there's a couple ways I could do it. My first thought, and I'll walk you through my thought process. My first thought is to use this, because if we add, like, let's say we reacted with HBr or something, the Br will go here, but the Br would also go here because they're both tertiary locations. So maybe to force this as like a major product, let's go ahead and move that double bond over to here. And now we can only add it here, if that makes sense. Although of course we could have done an alkyl shift, but again, you would have had tertiary and tertiary. So anyways, I like this. Let's react with HBr. And we know this double bond will grab a bromine and put it on the more substituted spot. Here we have a chlorine in the more substituted spot. So if we're starting with an alkene, we don't need to go crazy here. You can just add HCl. And you'll get the chlorine on the more substituted location. And then for this one, this is all 3 of these ethyl groups are the same. We just added a bromide somewhere. So I'm just going to go ahead and say, make one of those a double bond. Okay, so if this is an alpha, this one would have been the beta right here. And that also would have occurred with HBr, so not too crazy. Darn, I was hoping for more fun. All right, y'all, I hope this helps. Is that everything? Oh, just kidding, it's not. Let's keep going, good. I was a little disappointed by that last one. Oh, okay. Okie dokie, let's do stepwise mechanism for this sucker. I'm gonna get paper. Okay, so it says we actually know our products, we know our reactants, and we even know what we're using to make the conversion occur. So let's think about how this worked. Okay, I got a methyl group right here coming off this ring, and right now I have one. Let's start here. Chances are that this oxygen, let's just call that oxygen 1, okay, and it's going to be attached to some carbon named 2, and then 3, 4, 5, 6, 7, right? So that's 3, 4, 5, 6, 7. So if this 1 right here is our oxygen, that's going to be this one. And we notice that there's a methyl group coming off, meaning one of these carbons have to come off. What that tells me is chances are there was a carbocation right here, and that's what the oxygen went to and grabbed. Okay, so the oxygen went over here and grabbed it. That's the only thing that would have forced this methyl group to come off. So I want to find some kind of reaction that takes that oxygen and attacks that, right? In order to do that, we're probably going to want to form a carbocation. And that's super easy to do because we know that that H2SO4 can do that, especially when you have an alkene. So that's why we get these racemic mixtures and things. So let's go ahead and start like this. Okay, and let's start by reacting with H2SO4. Remember I said we like to kind of break it up like this. Now remember the double bond acts like the nucleophile. The double bond is going to grab the hydrogen, forcing this on there. And what that's going to do is it's going to push. This would have the hydrogen on it now, but it leaves this one all alone. Why this one? Because that one's a secondary, so it makes most sense. That's going to be the more stable one. If it could move around, it would, but there's no choice. It's either primary or secondary, so it's going to stay at the secondary position. That got us pretty far, right? Because now this thing is already primed to attack. It's got that lone pair of electrons. So there's nothing stopping it from going whoop and attacking. And when it does that, if I draw this oxygen like this, I got 1, 2, 3, 4, 5 carbons, and then I know I'm going to have one sticking off. 1, 2, 3, 4, 5, and one sticking off. Oh, that works really, really, really well. So that is exactly what we would get. But we'd still have an H on here, and this would be positively charged. But that's cool because this was just added as a solvent. It wasn't even one of the reactants. It's under the arrow, right? Which means we should be getting it back in the same way that we left it. So we still have this HSO4 negative, and what's going to happen is that can come back and grab this, and those electrons can go on there, and then we have the final product. Yay! Not so bad. I like these because you can mess up a lot and you can just see if it works. And if it doesn't work, you can go back and try to figure it out. But pretty much when you add something like H2SO4, strong acid to alcohol, there's two things that can happen. Either this oxygen will grab the H and it'll be a good leaving group, so it'll be great for SN1 or SN2, depending on the situation, or the double bond will grab an H. Okay, let's keep going. It says, what is the product of the following reaction? Oh darn, we kind of already know this. Let's make it more complicated. Let's put this on a dash here, just so we can remember stereochemistry. So when we're adding a Cl to this, remember this would work with a primary or secondary Cl addition, and this occurs via SN2. So we should expect the inversion product with chlorine on it. Here we have a tertiary thing. We're adding HBr. If you remember, if we have a tertiary alcohol or secondary alcohol and you add HBr, that's when you're going to get via SN1. So you'll have both products. So you have one where the bromine is on the wedge, and one where their bromine is on the dash. Okay. These boxes are not nearly big enough to draw. So if they show up on your exam, just draw outside of them, unless you're, well, you guys are all better than me at drawing, so never mind. All right, and last but not least, we have this. Kind of what we just talked about. If you take this thing and react it with a strong acid, that's not an alkyl acid, so it's not an HX, but like H2SO4 is the main one we did, or TSOH. You can get this. So we could have done either of those, H2SO4 or TSOH. Either one of those would have made this a better leaving group, and then they would have come back and grabbed an H. Okay, last but not least, very similar to what we just did up here. Now we're taking TSOH. We already know it's going to make this a good leaving group, and it can occur via E2. And we'll get the E2 product, which would be that, as the major, and you'd also get the minor. Cool. All right, now I think we're done with this. So I hope this helps, and I'm looking forward to going over it in class if we haven't already. So I'll talk to you later. Bye, y'all.